My name is Emmanuel Bernabe, and today's show is brought to you by Big Plasma AI. That's my company. We help mid-sized manufacturers and OEMs go to market with new predictive analytics services that involve AI and machine learning. So if that's something that you're interested in, head over to bigplasma.ai and find out how you can go to market as a lean operation without having to recruit a big giant data science team or build something that your customers are not going to like. So head over to bigplasma.ai for more information. All right, so now let me introduce my guest, Vid Jain. He is the founder and CEO of Wallaroo. Really excited for this talk. Wallaroo has had a great year. They raised a Series A earlier this year, headed up by Microsoft's venture arm M12. And most recently, they announced the winning of a contract with the U.S. Space Force to help with predictive analytics with satellites in orbit. So awesome year for Wallaroo. I'm really excited by about the problem that Wallaroo is solving around deploying AI models and machine learning models. Having been a practitioner for some time now, I can tell you that that is a real major pain point, and it's a bottleneck for getting at ROI for data science and machine learning for a lot of companies. So really excited to be talking to Vid. So with that, let me bring him on the stage here, and we'll have Vid say hi and introduce himself.
Hey, Manny. Thanks for having me on the show. I'm really excited to talk to you and to talk to your audience. Here to answer any questions as well.
Awesome. Thanks for coming on the show, Vid. Let's start off by telling us a little bit about yourself. Tell us a little bit about Wallaroo.
Yeah, okay, thanks. I came out of academia, actually. I guess I never imagined I'd be doing what I am. I have a PhD from UC Berkeley. But I ended up in New York, and if you're academic and you're in New York, they make you work on Wall Street. They handcuff you to that for a bit, and so I did that for close to 9 years actually, and helped build the high frequency and automated trading business at Merrill Lynch. I was part of a product group that was in the business that basically build a set of technology and product solutions around trading and risk management, and that was all very much machine learning based, right? That was, I guess, the huge kind of exposure to large amounts of data, very, very fast data, and using machine learning to actually deliver the business value. And I think the experience there that had a big impact on me was the fact that it actually took a lot of work to get value out of all that research and development that we did. And there's this funny diagram that kind of has been going around the internet that I think the VCs have been commenting on. There's like on one side you've got data, then in the middle you have AI, and then data plus AI equals value, right? So conceptually, that's right. Like, that makes sense. Everybody, the reason everybody's excited about that is that does make sense. Data plus AI equals value. The funny thing about that is it makes it sound like you just plop that data into AI and out pops the value. In fact, what we learned at Merrill Lynch, and what I think a lot of other customers and people that we talk to are learning, is that last part of getting the value out of that is actually really hard, very, very hard, lots of work. And and that's what I decided to tackle after I left Merrill Lynch. I'm like, okay, that's a nice meaty problem. It's a real problem. It's a problem that everybody's going to have, whoever's working on machine learning, and we're going to make that easy for people. So that's kind of the short history of myself and sort of why we're doing what we're doing.
Very, very neat. And Wallaroo had some really cool news earlier this year around the landing of a contract with the U.S. Space Force. Can you tell us a little bit about that? What's the use case there? What are you looking to do there?
Yeah, so I guess you could say, there's a lot of talk about edge. I'm sure you've heard about edge computing or edge machine learning. And so that's the idea that AI is not just going to run in large, giant data centers or on-prem, but everything is going to have AI in it. You're gonna have smart everything, right? Smart
Right.
coffee machine, smart fridges, smart cash registers. So edge just simply means that this um, machine learning. You're not necessarily just going to bring the data back into the cloud, but in some cases, in many cases, you're going to actually run that machine learning. You're going to make the predictions where the actual data is being generated on the sensors, on the coffee machine, on the refrigerators. And in the case of space, that edge is really that distributed environment that supports all the space efforts that we have, right? And so that's satellites, that's space stations, that is land-based systems that support that, and it's a very distributed environment. And because of security reasons, because of latency reasons, because of bandwidth reasons, sometimes these things don't have very good connectivity to the home base. You need to have that machine learning running right there. I guess if you're a movie fan, I love 2001. Right? I don't know if I've seen that thing like 10 times. That's
Totally, it's
probably
amazing.
that's the extreme example of AI in space, right?
All right.
Where it takes minutes and minutes for any kind of communication from the device, the spacecraft, back to the home base, right? And so you've got
Right.
artificial intelligence there, supposedly helping the astronauts, and so this is kind of a step towards that. Obviously, we're not talking about some kind of fatalistic AI, but really keeping these things working well, predicting if there's going to be any failures, enabling the humans and the astronauts to be more productive, to automate some of the tasks that they might otherwise be asked to do. That's the goal of this, is to really improve the resiliency, the performance, and efficiency of the space, all our space efforts.
Awesome. That makes sense. And when I looked at the news, it seemed like it was around predictive analytics for maintaining satellites in orbit. And of course, that's a great use case for AI and machine learning. In manufacturing, for example, if you can anticipate when something is going to fail, you can do predictive maintenance rather than reactive maintenance. If you wait for that thing to break down, that can create a big bottleneck in your operations. It can shut down your operations. And for a lot of manufacturing processes here on Earth, okay, that's an inconvenience. You have to call somebody in. They have to bring their tooling and service it, and you're down for a day. But if that happens in space, the next time that
Right.
a servicing opportunity might not be for several months, if not years. So tell us a little bit more about the predictive analytics part of this. How are you looking to anticipate when things are going to fail? What's kind of your strategy there that you're looking to leverage your technology to do?
Yeah. So that's as you already mentioned, that use case is very, very general. It's not just space, it's manufacturing, it's, even the cars that you drive, right? So car manufacturers looking at putting AI in the cars for safety, for predictive maintenance, for things like that, aircraft, right? So any kind of craft, obviously, but also, any object or device that could fail. Manufacturing certainly is another use case. So this is a very general type of use case. It just so happens in this particular scenario, those things are floating out outside of Earth, right? But otherwise, as you said, it's a very general use case. So the one thing I do want to clarify is, so if you think about machine learning and how it works, right? There's really three parts of it, right? There's the data, right? And then there's the development of the machine learning models, and then there's the deployment of those models against live data. And so what we don't do is we don't actually develop models. We're not people, right? So what is a model? A model is basically an algorithm that finds patterns, right? And those patterns hopefully have predictive failures. I mean, have predictive, yeah. predictive properties, right? So, so for example, if you've got all sorts of, in the case of satellites, if you've got all sorts of data from sensors in the satellite, and when you see a certain pattern that predicts that something in the satellite is going to fail, and you see that happen, say 99% of the times, then you have a very good chance that if you see that pattern again, right, that's going to predict a very high chance of failure yet another time, right? So that's called training a model, right? That's basically giving the model data, and then which is historical data, and then it figures out what the patterns are, and then those patterns, the model is an algorithm that basically will tell you, oh, I see this pattern, now what should you do, right? That training part, we don't do. The thing that we do is, if you're a data scientist, for the Space Force, you're a data scientist for the government, or a data scientist for a manufacturing company, you're a machine learning engineer. What we do is we help you operationalize those models, right? Basically take it from the lab environment. So the lab environment is, you've got some historical data, you got like an R&D thing, the data scientists are trying this thing, they're trying that thing, they're doing crazy stuff, maybe, who knows, but at the end of it, they have something which they think is pretty good, that has really good predictive power. But now they have to move it from that lab environment. They have to take that piece of logic, that algorithm, move it into the live environment where the live data is, and integrate it into all the other workflow, right? So, because it's not just like you have to get the data into it, you have to get the prediction out of it, you have to do something with the prediction. That thing is useless if all it's doing is making predictions and they just go nowhere, right? And so you have to take it out of the lab, you have to move it into that production environment, in this case, the satellites or whatever, where it needs to run, and integrate it into the overall application and workflow that you want to achieve, right?
Yes.
And so that's what we say when we want to make it operational, and that's how you generate any kind of value. Sitting in the R&D lab, it doesn't generate any value, right?
Right.
And so that's what we do. We help you take that model, or several models, or however many things you have there, help you take those into that live environment, and actually get it to work against that live environment in a way that is generating that value, right? And so one aspect of it is doing that movement and integration into that environment. The other aspect of it that people don't understand, if they're not living this and practicing this, is that machine learning, applications which are dependent on machine learning, or which have machine learning embedded in them, are in some ways very different than standard application deployment, right? Because the data, they all depend on the data, and the data has various assumptions, it has a various shape, and so they're only as good as the data. And so you can't just put them there and forget it. It's not a set and forget, right? It's almost like a living thing. It's almost like a farm, right? You have to keep watering the thing. You have to keep monitoring the thing. You have to keep tweaking the thing. You have to dig the weeds out. And so with machine learning, the assumptions that went into, when you train that model, you assume certain things about the data going into it. Maybe it turns out that in a live environment, that those assumptions don't hold, right? Maybe it happens that there's drift, that maybe they hold and then they drift away, and they hold, come back, maybe because you didn't take into account the way the sunlight hits the solar panels, when it's actually rotating out in space, that changes the kind of heat signature that these things are getting. I'm just making stuff up, but so it's not just a matter of creating something in the lab, because the real world is not the same as the lab.
Right.
The lab is where you take your best shot, given the best data that you have in the lab. You develop something you think is going to be really good, but actually it's not until you get into production that it does what it does, right? And therefore, it's not just about, let's put it there and forget about it, especially with very highly expensive, very critical and device critical environments like the space or with other craft, you have to make sure those things are up to speed. They're working in the way that's acceptable. If there's an issue, you have to catch those issues. You have to troubleshoot them. You have to maybe tweak or modify those models, right? So
Right.
again, a lot of people think it's like, oh, I do some machine learning, I throw it over the wall, I'm done, right? And this, that's like, that never works,
That's
right?
just the beginning.
That's just the beginning, right? That's already hard, but that's already the beginning.
Right.
The really hard part is that, what we call that last mile, which is getting into production and then massaging it, tweaking it, monitoring it, troubleshooting it, iterating it. And that really becomes an ongoing thing, right? And so that's what we do. We're not a professional services company. It's not like we bring 50,000 people and say, okay, we're gonna work on this like Accenture or something like that. We have a platform, right? And we have a platform that's developed with years of experience, both from my background, but Chris, our VP of engineering, comes from Data Robot. Our Eunice, our head of product, comes from Tempest Labs, a unicorn startup, raised $1 billion from Google, et cetera, to disrupt healthcare AI with AI. So we have different backgrounds, but we were practitioners, right? We were
Yes.
practitioners of this thing in the real world, where we were like, okay, this is what you need to do it right. We want to bring that to everybody else, right? And so I want to make sure that people understand what we do. We don't develop the model. We're not developing the model that says, hey, if I see these solar panels do X, Y, and Z, one of them's gonna die, right? That's not what we do. What we do is, once you figure that out, we let you get that into production. We give the tooling to catch any issues, to optimize that in a production setting, to manage those in a production setting, and ultimately to get the outcomes that you want, right?
That makes a ton of sense. And yes, having been a practitioner, that is a major pain point. I think when I first started off in data science, I spent a lot of time on collecting the data, cleaning it, building models, picking the right algorithm, the right hyperparameter tuning, and all that stuff. But now I'm always asking myself, okay, where is this going to be deployed? And can we deploy it really, really fast to find out the inevitable bugs that are going to happen when we try to push this production?
Right.
And I like the points that you highlighted. Yep, this is pro advice. As you're looking to get ROI or return on your AI and data science investment, you need to try to deploy, and you're going to have problems around the environment in which your model is being deployed, because your data scientists may have trained this model on their notebook or on their cloud infrastructure, and that's great, but that's not where the model is going to live. It could live on a server on a factory floor. It could live on a low-powered edge device in space. It could live somewhere else in a very inhospitable environment, without connectivity, without access to data, without access to compute. So you always have to ask yourself, what is the production environment in which this is going to be deployed? And then I also really like the fact that you mentioned integration, because you're right. It's kind of like, does a model really exist if no one takes action on an insight? I would say no. No, it's not. You get deployed and it's firing. But if that insight, that output, that prediction isn't being put in front of an operator, and that operator isn't taking action on that, then you wasted a lot of time on that particular model. So 100% agree. Integration, monitoring that is key. And then your third point around data pipeline management, absolutely key. I can't tell you how many models I've deployed where the assumptions that I had about the data, its availability, going into the model versus what actually ended up being the case were night and day, and they made all the difference. You see this everywhere in finance and manufacturing, in all different types of spaces. So that is really, really neat. And so all those pain points I've lived and I can appreciate. Can you tell us a little bit about how Wallaroo is doing this? Given your years of experience and dealing with these problems, what are sort of the key functionalities and tools that a data scientist is getting from the Wallaroo tech stack to help address some of these pain points?
Right. So I think there's two questions in that. One is kind of our overall philosophy and how we approach these problems. The other one is I guess more technically, like what does the product do and how is it doing it, right? So I'll start with the first one, which is really, there's a lot of things out there. There's open source. There is things like Databricks and Spark. There's other technologies that people use and other products. And so one of the things that our philosophy was that a lot of this stuff is too hard for the actual practitioners to use. Like you need a giant like operations team, and you need a lot of infrastructure sometimes, and there's a lot of complexity. So our first starting point was, this is way too hard. Like as practitioners, we use a lot of this stuff, right? That was already out there, and we're like pulling our hair out, saying, "Oh my God, this stuff is so hard." And that was actually the genesis of the company. Was like, why don't we build something that we would want to use, right? Because after leaving Merrill Lynch, I started a consulting company, and we're actually building data and AI applications, and we're using all this other stuff, and we're like, "Oh my God, this is so hard." So our philosophy was really centered around simplification, ease of use, and then thirdly, scalability, right? And people think of scalability in a very narrow sense. They think of scalability as just more and more data, right? More users, if I have more data, I have more events, and so that's one way of scalability. But scalability also has two other really important considerations. One is repeatability, right? If you're dealing with operations, right, and you're doing something over and over again, that means you need repeatability in order for you to scale, right? If you have more use cases, you have more data scientists, you have more places where machine learning needs to run. You need easy repeatable processes and tooling to enable that, right? So that's one way of scaling. The other way of scaling was it's again not just about more data, but it's about more and more use cases, about more variations of the model. It's about more places these models need to run, more satellites, more cars, more whatever, right? So we sat down. We started with like, okay, nothing out there really that we've tried hits these points. Easy, simple to use, uh, uh, powerful and flexible, scalable in all these senses of the word scalable. So we started with that. We started with like, okay, we want to make it easy for a data scientist and an AI team to do all these things that right now take days. It requires a big engineering effort. It requires a bunch of, engineering and ops support. Like, how do we make that simple, right? Number two, we want to build something where it could be this Space Force, it could be cars, it could be a giant data center, it could be a huge cloud thing where you've gotten, ad tech where you have a trillion events a day, right? So we want to build something that's like that. And so once we started thinking about it, we realized that we had to start from scratch. We had to re-engineer this thing, whatever this thing was. We couldn't just take existing tooling and cobble stuff together, right? We had to build something that was for the future, not take something that was 10 years old or 5 years old and cobble it together. And so one of the first things we did is we said one of the core things that machine learning needs to do in production is it needs to do what's known as inferencing, right? You know this, but I just want to make sure that the audience knows what that is. And the inferencing or the scoring really means you give it some live data, the model runs against that data and produces a prediction, right? That's the inference, right? It's inferring that it's fraud, or it's inferring that there's a failure happening, or it's inferring that whatever. And so that engine, that compute thing that runs that, it's computation. It's computation over and over again. One of the first things we did is we said that thing that takes that algorithm, runs the computation, it needs to run everywhere, and it needs to be super high performance because we need it to run in some obscure edge environment, which is maybe not much different than a Raspberry Pi, all the way to like trillion events a day and complex algorithms, etc. Right. So the first thing we did, the place that we started, was we built an extremely modern, very high performance, very low latency, distributed computing system, right? And so again, I'm using a lot of technical buzzy words. Let me just make it simple, right? What is distributed computing? It means, like, for example, Databricks or Spark is an example of that. The reason you use that is to abstract away the underlying infrastructure. Like, it doesn't matter how many CPUs or servers that you're running on.
Right.
You don't need to worry about it. The system takes care of it. It breaks up the work into little bits that can run across the distributed computing that's available, right? At the same time, it had to be distributed in that sense, but it also had to be distributed in the sense of edge, where you might have 60,000 cash registers and the computation is happening at the cash registers, right? And so we built this thing in a language called Rust. Originally, we didn't build in Rust. We built it in some other esoteric languages, which are super high performance. So eventually, more recently, we rewrote the thing in Rust. So we built this thing to have very, very high performance, right? And at the same time, you can stick your Python models in it, right? And you can stick your C models in it. You can stick a lot of different things in it. But we built this thing to kind of manage that distribution of the work, the resiliency, the failover, the capturing of the data for the observability, like all the other stuff, the standing up the infrastructure when you need it, shutting things down, load balancing. Like, it does a whole bunch of things, right? Things that, but it does them very, very efficiently, and it's designed to run, and almost any kind of machine learning model in it. So that's the first thing we wrote. That was a lot of work. We wrote that thing 4 times. We kept testing it. The first version of it, we used to build little clusters with Raspberry Pis. We actually had bought all these things, and our developers at home, they had built these little homemade clusters that were like, each node was a Raspberry Pi, and we would test it on that cluster, right? Because that's how efficient we wanted to be. And because we put in that effort at the beginning, it turns out we can address a whole host of use cases that existing technology can't, right? I think we're unique in that thing, that right from the beginning, we said, how do we build some core inferencing engine that can scale all the way from a little Raspberry Pi to a giant cluster in a cloud or in a data center, right? And make it very efficient for large batches or for very fast streaming, real time. So that was the thing that we first built. The problem with that thing is, while it's very, very fast and very performant and can do a lot of amazing things, it's not easy for the data scientists to use, right? Number one. And number two, as you need to know, you can't fly blind. You can't just throw a model into production. You have to see how it's doing. You have to have all sorts of testing, right? So then that was the core. Then we built all this other scaffolding around that core. We built self-service tools that integrate into that core, there's an SDK for the data scientist, there's an API for enterprise integration, there's a UI for data analysts. We built all these self-service tools where you can go and do very powerful things with a click of a button. The big green button. You go there, you push the button, you deploy a model, or you can write a line of Python and set up an experiment, or set up a A/B test, right? And then at the other end, we built a whole bunch of analytics and audit capabilities. And so this approach of starting with the core, building a very high performant core, and then building tooling around that core for ease of use and for deep and advanced observability, that's where we ended up. It's a very modern platform. It addresses a lot of different use cases, but it started with core, like, engineering and architectural chops from the beginning.
That makes sense. And if I'm a data scientist, I'm going to like this, because as a data scientist, I want to spend as much time on those first 2 nodes of the workflow that we talked about, getting the data and training models. I think that's what data scientists love to do. And Wallaroo gives me an option to, with minimal effort and ease of use, to be able to also take care of the stuff that I have to take care of, as a responsible data scientist and operator in terms of deploying and monitoring all the different models. So from a data scientist perspective, I totally get that. And if I'm a business unit leader, I like this as well because I don't have to go out and hire an even larger team of ML ops engineers, right? Because if you have to support this on your own, you need to get a whole bunch of engineers to stand up all this infrastructure and do all the monitoring. And that's going to be tough to recruit. That's going to be tough to stand up, and it's going to be tough to maintain. So if I can have more self-service tooling that makes this easy for my data scientists, that's going to be a win for me. Is that fair?
Yeah, I think the only other persona I would include in that is actually the ML engineers or the ML ops engineers. They actually like us as well, because we make their lives easier, and we help them get more done in the day, right? And so I would say the business owner, the data scientists, and the ML engineers are all people that we're trying to provide value to. So I don't want to leave them out because, frankly, we rely on them. As we come into organizations, we integrate, and we work very closely with the ML engineers or the ops people there to make sure that this is successful. And our best and most successful engagements are where they're involved from the beginning, right? And they value us too because they make their life easier. So I just want to make sure that we don't leave those people out. They're very important as well.
That totally makes sense. And no, I'm glad you included that persona in there. That makes a lot of sense. And to the extent that we can help leverage these folks, because they're very hard to come by, and help them do more with less, and help them plug into the broader effort and team in a seamless way. And if you have one place to do that, a platform to do that, I can see that being very helpful. And so I think, when we think about ROI, getting the ROI on a data science investment, that's the denominator. That's the investment part, which is typically people and tech stack. So that makes sense. I also like the focus on extending out a model to different types of environments and different versions. So I would think that's almost more on the numerator side, the return part, where if I build one model, then I can extend it out across different use cases. I can extend it out to different types of deployments. So if it sits in the cloud, I can just rewrite it so it sits on an edge. So that to me is very interesting and very compelling. It used to be that if I wanted to do that, I would have to rewrite that model every time. And that would be kind of a pain to do that for all those different types of environments and use cases. And that's part of the problem that keeps data science from being scalable, is that now I have to rewrite this whole thing and go through the whole effort and train it and deploy it. So I'm wondering if you could tell us a little bit more about that. How are you seeing companies leverage your technology to do that, so that I don't have to rewrite models again and again and again, and I get the most out of my initial efforts?
Yeah, so I think our job is to empower the data scientists, the machine learning engineers to do more, to deliver more value, to be heroes, right, internally, right? So obviously, if they get stuck and there's nothing getting into production, or nothing scaling, or the value is not coming out, then at some point even the CEO is like, what's going on, right? So our job is to really empower these people, and so let them be bolder, right? If something succeeds, they can be bolder. They don't need to be afraid that something's going to fail. So there's some obvious things, like, unless you think about it, you're like, and once somebody tells you that, you're like, oh, actually that makes sense, right? So a lot of times, you need scalability in the sense of, like, you need to take something you've done once and do it 50 times, right? And not because you've got more data, but, like, here's a very simple example that you don't necessarily think of. Let's say you're operating in Europe. And in Europe, you have these data privacy laws, very much more stringent data privacy laws. So we've come across people that are like, hey, I have a customer, I've got my own customers. And so I've got to do the same thing. I'm doing this thing, for these 20 customers, but these customers themselves are operating in these different countries, 20, 30 different countries. And I have to segment the pipelines, right? Because I can't intermingle that stuff. So all of a sudden you take 20 times 20, you have like 400 things, right? So let's say you've got, you're a manufacturer, and you've got, or your CPG or whatever, and you've got customers, that are maybe buying your product and they're selling it to the consumer, right? Maybe it's a supermarket or something, right? And so let's say you're trying to optimize, how do you optimize some kind of forecasting or production thing for that supermarket. But the fact is, you've got multiple of these customers that are buying your stuff, and they're operating in different countries. So it multiplies, right? So all of a sudden, instead of one model and one production pipeline, you have to make variations of that model and tweak it a bit for every one of these scenarios. And now all of a sudden, you have several hundred pipelines, right? So that becomes that's a scale in the sense I have to repeat the same thing over and over again. If you imagine you have to do that manually, right? If it took you, 2 weeks to do the first one, and every one is 2 weeks, and then you need to monitor them, and you need one person to sit there monitoring each one, right? That's going to take you like 5 years to do, and you're going to need like hundreds of people to sit there monitoring what's going on, right?
Right.
So this kind of scenario and so what happens is that people limit what they're doing. They're less bold. They're less willing to do complex things because it's complex, right? And so therefore they limit the potential of the AI. They do the simplest things, right? Because they're having so many challenges doing this more sophisticated stuff. So our goal is to let them go crazy. Let them do just click, press, make a copy. Click, press, make a copy. Go to the dashboard. Go see how all these models are doing, right? And so when you empower them, they're free to actually do what they really want to do.
Right.
Right. And so, that's our goal. And so this idea of like being able to repeat the same thing and create different variations and have different use cases and try different things. And don't be afraid that it doesn't work. It doesn't work, great. You click the button, you undeploy it, make a change, redeploy it, run an A/B test, So that's really, I think one of the things we're seeing is because people are being so constrained with the tooling that they had, and because it takes so much effort to get stuff into production, and because they're limiting the possibilities, right? And we want to kind of empower them to be bolder. We want to empower them to get value faster. We want to empower them to kind of really deliver for the business.
I think that's right. It's going to limit how bold, to use your word, a data science is going to work. I think it's going to also, in my experience, it slows down the innovation cycle. So when deployment is such a bottleneck, I have to wait 3 months for my model to get deployed. Like, okay, I wrote this Python model. It took me a month to build it and to validate it. I love it. Now I throw it over to MLOps, and it takes them 3 months to deploy it. And I have to like spend time with them to recode everything and to translate everything, and it's not what I wanted. And then I find out 3 months later there's no value to it. So I think it slows down things quite a bit if you have sort of an ad hoc, rudimentary way of deploying these models. I think also the other problem that I've seen as well is teams try to tackle this by throwing more bodies at the problem. So you get more ML ops engineers to sit down and translate everything into the native language from Python or R, and that slows things down as well. And it's not an enjoyable process. So that makes a lot of sense.
And there's business risk too. I mean, I was talking to somebody at a bank, and I want to mention who it is. So they had developed some stuff in Python. And the team that was responsible for operationalizing it didn't know what to do with that Python. They're like, oh, we can't put this into production. So they rewrote it in Java. But they had issues like with the thing. This was a regulatory application. It was supposed to monitor transactions and stuff like that. And so the Java thing that went into production didn't work correctly. Ooh. And so they had all sorts of investigations. They had a fine, it was a multi-million-dollar fine, right? So this is not. It's not just like from a business perspective. There's also risk involved, reputational risk if this stuff doesn't work. There's financial risk. There's also some risk there as well, right?
Totally. Yeah, that's a great example. That's right. Some of it gets lost in translation, and you might not find out until you get the regulators knocking on your door. Um,
Right.
uh, Let me ask you a question, Vid. When, if for companies that are just getting started with AI and machine learning, they're putting together their strategies, they're putting together their teams. Um, I guess the question is, when should a company be thinking about deployment challenges and deployment strategies and all the things that we're talking about? At what part of the process is that a good time to come in and start thinking about that?
That's a really good question. It depends, I think, a little bit on the experience of the team, and it depends on the complexity of the use cases, right? So I do think what we're seeing is that most companies uh, wait too long to start thinking about that, right?
Right.
You shouldn't get to the point. It's not like you can flip a button, right? That like, hey, now I have these models in my business head or whatever is expecting like revenue tomorrow, right? These things do take time to operationalize to get value out of them, and so you need to start that planning sooner rather than later. That's not to say you should start it like a year before your plan says you're going to get there, but I do think people tend to wait too long, right? And also you want to get the team familiar with the processes, familiar with the operationalization, and also it's again going into a production environment is not simply like here's a prototyping or lab environment, then the next environment is production. There's usually maybe some steps in the middle. Like there's at Merrill Lynch we used to do validation first. We used to what we call back testing. We used to take whatever we developed and test it against 2 years worth of trading data, and then when we felt comfortable, then we would put it into a staging environment, and then once we were comfortable in the staging environment, we would roll it out slowly into a production environment, right? So you also need to think through like what does that look like from a lab environment into a production environment, and so we're not just the production. We can be the validation environment. We can be the staging environment. We're just not training, right? So uh, there's so many times where like the customers will not think through that, and on the other hand, what happens also sometimes is people have built stuff, their own tooling. Most companies build their own tooling, right? They're not using Databricks, they're not using Data Robot. Most companies
Right.
are actually they hire a bunch of people, very smart people, very good people, that spend a lot of time building this stuff. At some point, that stuff doesn't scale, and so people also wait too long, and the business is growing, it's successful, and then all of a sudden you hit a wall because of what you built, and then you have to retool it. And so they wait too long to think about what should that thing look like? How do we re-architect it?
Okay.
And what is our core competency? What is it that we're good at versus what is somebody else good at, right? And I think as a technologist, I always want to build cool shit, and I understand. I
That's
understand why
urge.
I want to build cool shit. Like nobody wants to be doing boring stuff, but I also think at some point stuff becomes a commodity, and versus where the business value is. And I think a lot of organizations are not good at figuring out where that line is.
I gotta highlight that. That is absolutely key. I think I like your phrasing. Most companies are waiting too long. So if you're a business unit leader, or if you're leading one of these initiatives, do it before you think you have to do it. Start thinking about deployment before you feel like you have to do it. But because by and large, you're gonna wait too long to think about that. In my view, I always want to deploy something that's minimal at the very least, as soon as possible, to find out all the inevitable issues that come with deployment. There's always some integration issue, like, oh, like I can't plug into this system, I can't pull this data, because of XYZ. Like I don't have the power there. Like there's always stuff like that you should try to discover as soon as possible in your process. So I'm generally in favor of doing that like very, very soon before you get too fancy into your algorithms or models. Try to deploy something at a very minimum. And I think I'm laughing because your point around building it in-house, yes, like, oh my gosh, for some reason, I don't know, I can't explain it, but there's always a bias to try to build it in-house. And I don't know if it's engineers that want to like play with the latest tools and add it to their resume, or business unit leaders thinking that they're going to have more flexibility, more IP if they build it in-house. But yes, I would totally fight that urge. Always try to think about what you can use off the shelf that's available to try to deploy this and streamline your process, and just appreciate that your core IP, the value that you're bringing to the table, it's probably not in deployment. It's probably not in monitoring. It probably has to do with the data that you have, the way that you're processing it, the way you're presenting that to the customer. That's your real IP. So if you're going to focus your time and energy and spend, it should be on that part of the process. The cloud compute, the training, the staging deployment, that stuff you should try to look for tools like Wallaroo to help you implement it and to deploy.
Yeah, no, you're absolutely right. But at the same time, as somebody that, is close to technology and loves technology, I don't, I can see myself like why it's kind of cool and interesting and whatnot. I do think once you reach a certain stage, though, or even if you're very early, from a business perspective, you want to figure out what's the best way to use your people and what's the best way to actually get to where you want to get to in the fastest way to do it, right? So I think, again, I can totally understand why, I mean, our engineers come here because they want to do cool stuff, right? That's the attraction. And they're like, oh, we love Rust. We want to learn Rust. We've hired people have come here because just the attraction of the language that we're working in, let alone like the space that we're in. So I can understand that. But it's always going to be a balance, I think, between that and what is the best way to get to the outcome.
Awesome. We got a question from the audience here from Hector. How do we do benchmarking? Can you talk a little bit about that? And I'll give some context. If a data scientist, rather from a data scientist perspective, what's the value of a particular model? What's usually compared to something else? So it's a model that's compared to a rule, or it's a more complicated model that's compared to a simpler model. But you have to compare models to one another to see whether or not you're getting alpha or value from that new model. So can you talk a little bit more about how you think about benchmarking on the Wallaroo platform?
Yeah, so we think of benchmarking in two ways. One is exactly what you said. How do I basically bake off different approaches or different models? And the other one is just from a value perspective, is performance. A lot of times our customers care about performance or scale, right? So those are the two ways we think about it. To answer the one that you explicitly said, we have a very flexible and powerful A/B testing framework. And so what you can do with a line of Python, for example, from your notebook, is you can define, hey, here's 4 models that I want to bake off between a model A, model B. So you can write a line of Python that basically defines that test, and then you write another line of Python that deploys that pipeline, and gets it into that environment, and you can go and see the results in real time, right? So, and there are different kinds of tests you can do. You can do basically a champion challenger. You can do what we call shadow deploy, where you have one primary model and you have other ones that are kind of following it. You can do things where you can say this, if you had a credit card fraud model, you might say, if this is a platinum holder, they get this model versus that model, or so we made it very flexible. But the idea is that basically you can do this kind of bake off and benchmarking against other models or against historical very easily. You can also do things like what you might would do, going back to my trading days, is maybe what you want to do is you want to run 10 models continuously. One is doing the actual trading, the other 9 are just shadowing it and producing results. And when you see that, for example, this model that's kind of one of the shadow models, it would be more effective at the trading, you can just flip the button and switch, right? And so you can also have this way of like more easily optimizing your machine learning in a production environment to actually increase the the value of what you're doing. So that's one way in which we do allow you to do kind of benchmark different things and different models against each other. The other way of thinking about benchmarking is just raw performance, right? And so we measure throughput on per machine learning pipeline, per server, per CPU, per model. We measure latency, compute latency. And so whenever, quite often we're asked to benchmark these things by customers, because they're like, okay, I have this NLP model and I need to run it on this data, and I'm doing it in a Databricks cluster, or I'm doing it on AWS SageMaker. Can we compare, right? So we give them reams and reams of data. We collect that data automatically. It's not like we have to set up anything. So they can see in real time, and they can be like, oh, wow, that's actually, 12 times the throughput and using, a fifth of the infrastructure. Like, wow, so that's the other way of benchmarking. We built that in from scratch, so people can see in real time how the thing is doing.
Very neat. I wanted to touch on one more topic before we go, because I think it's really important. If you have a couple more minutes, Vid.
Yeah.
Edge and integrating that back into a central data science process or value add. I keep telling my colleagues and my clients that what you're trying to do with AI, you're trying to build an AI flywheel where you have data that is continually coming in and helping you build better algorithms to help you build more value. And a lot of that data is living on the edge, but it's problematic in terms of getting that and integrating it really well into a central type of framework. I know you've done some work on that. How do you think about that? How do you think about solving that problem?
Yeah, that's it. You bring up a really, really great point, because a lot of people, they just think, edge, and they think cloud, or they think on-prem. And really, when you're doing edge, you're not just doing edge, right? Because you've got this distributed environment. You got all these cash registers. You've got all these cars. Well, it's not like the data scientist is living in the car, right? And data scientist is somewhere else, right? But that model, sometimes that model, needs to be centrally managed. It needs to be centrally observed. In fact, often that's what you need to do. So we kind of think of it almost like an octopus, where the brains are in the cloud or on some centralized data center somewhere, and the tentacles where things are happening are at the edge. And so you have to tie the two together, right? So it's not just about running inferencing at the edge. It's about how do you manage what's running, how do you observe what's running, how do you retrain and redeploy, how do you automate some of those processes in a much more coordinated, centralized way. And then the other thing you have to realize is, if you're doing inferencing at the edge and none of that comes back into a central spot, you're never going to have learnings which are across all those things, right? Like, you can learn something in one car, or you can learn something in one satellite, or you can learn something in one particular version of something. But there's also stuff to be learned across all the cars, right? Or across many cars. There's like, if there's, like, you won't know necessarily that there's an issue in an intersection just from looking at the fact that one car is slowed down. Maybe the driver got out, or maybe fell asleep, or who knows what, right? But if you see all the cars are stuck at an intersection, you have much more information that, like, there's something at issue with that intersection. So you do need to bring some data back into a centralized spot, and you need to have further analytics and further understanding in that way. So you have to solve both that problem and the problem of running things efficiently at the edge. Part of it is not a technology issue. Part of it is knowing your use case and knowing what data and what stuff needs to happen in a centralized spot, and what data and what stuff needs to happen in an edge, right? Part of it is a technology issue of making sure these things can work both autonomously but also together, right? And the reason for both is that sometimes you don't have you need the car or the satellite to operate, even if the satellite link or the to the mothership is down, right?
Right.
Otherwise, then you're like your cell phone in the dead zone, right? You don't know what to do. So you need both of those things, right? And so we've given a lot of thought to that. I'll be honest, we're working on it still. It's not like we're at the end, we're like, here it is. But we're working on it together with some design partners, together with some really well-known technology companies and other customers. And so again, this is a very fast evolving field. There's a lot to be done here, but we're having a lot of fun doing it.
Awesome. Hey, I want to thank you, Vid, for coming on the show and telling us about Wallaroo. You're solving a major pain point in the data science workflow. So wishing you a tons of luck on that front. Tell us where people can get in contact with you and Wallaroo. Where should people be going to learn more?
Yeah, so go to Wallaroo.ai. And and then you can go to my LinkedIn. Just look for Vid Jain, VIDJAIN, and just connect with me on LinkedIn. And we can start a conversation. That we've got other ways for us to be in contact, all from the website, but Wallaroo.ai.
Awesome. Thank you again, Vid. Hey, everyone. Thanks for tuning in. Our next show is on the 13th, September 13th, where I am going to be interviewing Jimmy Sunny. He is the author of a new book called The Founders, which details the founding of PayPal and all the folks that came out of PayPal, Elon Musk, Peter Thiel, and he just tells the full story, which is fascinating, great story. So if you're a founder, I definitely recommend you tune into that show. That's going to be on Tuesday, September 13th. So look out for more details on that front. And with that, thank you, everybody. And thank you, Vid, for coming on the show.
Thanks, Manny. Thanks a lot.